this computer. Okay, so you guys already learned about force, moment, and resultant. And after that, you guys already learned about the equilibrium. And for today, we will use that for the Truss analysis. Okay, Truss analysis. What is Truss? Okay, when we talk about structure, sometimes we differentiate the structures into two. Most of the time, we can differentiate the structure into two types of structure. The first one is a frame and machine. Okay, that's the thing that we will learn after we finish about truss. Okay, and the second one is truss. Truss is like this kind of structure. I believe you have seen it by a lot of time. Okay, the structures which consist of small beam like that. Okay, such as the huge crane when they build the building like that, and in the rig, most of the time it's a truss structure. Beside that, okay. Yeah. Okay. Beside that, the one that is I believe most commonly seen is the structures that we normally find in the bridge. Okay, most of the time when we talk about bridge, it consists of truss structures. Okay, when you can see this kind of structure there, we call this structure as a truss. Okay, so by definition, when we talk about the truss, okay, by definition, truss is a structure composed of slender members, okay, joined together at their end points. So most of the structure that we normally see in the bridge is a truss, because you can see, right? It consists of a slender member. Okay, this part, right? The individual members, and all those individual members are connected to each other at the end. Okay, at their end points. Okay, something like this. Okay, this is an example of a bridge, simple bridge. Most of the time, the bridge is shaped like this, and you can see here, right? It consists of a slender member like this, a lot of slender member, and those members are connected to each other at their end. Oke, jadi bisa dikatakan kalau misalkan kita membicarakan terkait dengan truss ya, nah definisi dari truss itu apa? Truss itu adalah suatu struktur yang terdiri dari terdiri dari bim-bim yang kecil atau tipis gitu ya, dan dihubungkan satu sama lain pada bagian akhir dari bim tersebut. Jadi seperti ini, jangan kita lihat di sini, di titik akhirnya ini yang dihubungkan. Terus mungkin yang bisa kelihatan lebih jelas adalah yang di jembatan ini. Oke, ini terdiri dari beberapa member-member ya, yang dihubungkannya satu sama lain itu dihubungkannya di akhirnya, di ujung-ujungnya. Seperti itu, di titik yang saya merahkan ini, di ujung-ujungnya seperti itu. Okay, we will not talk about the flow of the force yet, but what I want you to learn here is what is truss. Okay, so that is truss. I believe you have seen truss in a lot of structures that you have encountered up until now, okay, like bridge or crane like that, or for someone who have followed their fathers to the rig, like in the rig like that. Okay, jadi saya yakin kalian itu sudah pernah menemukan struktur-struktur trust ini di kehidupan nyata sampai sekarang, ya, seperti misalkan kalau kalian kelewat jembatan atau kalian melihat crane seperti itu, atau di rig, ya, rig itu di lepas pantai seperti itu. Oke, nah itu adalah intro sedikit terkait dengan trust, ya. So that's a small introduction about trust. The most important thing that we will talk about today is how can we analyze the load which is happening at each member in the trust. Jadi poin utama yang akan saya ajarkan ke kalian hari ini itu adalah bagaimana kita menganalisis beban, ya, beban yang terjadi pada setiap member di suatu trust. Beban yang terjadi pada setiap member itu analisisnya bagaimana? Itu yang akan kita bahas hari ini. Okay, so when we talk about trust, the member in the trust and the trust itself, in order to simplify the calculation, okay, we have to make a certain assumption. Yeah, there are two assumptions here that we have to make in order to ensure that the calculation will not be that won't be that complicated. Okay, the first one is all loadings are applied at joints. Okay, and the second one, the members are joined together by smooth pins. Ya, jadi saat kita membicarakan trust itu supaya kalkulasinya tidak terlalu complicated, tidak terlalu jelimet, gitu ya. Kita harus membuat beberapa asumsi di sana. Nah, dalam kasus kita, ya, untuk yang akan kita gunakan ke depannya, ya, ada dua asumsi utama yang akan kita gunakan. Yang pertama itu adalah semua beban itu hanya diaplikasikan di join saja. Beban hanya diaplikasikan di join saja. Oke, kalau ada beban yang tidak di join, itu berarti bukan struktur trust. Oke, saat kita membicarakan struktur trust, ya, beban hanya ada di join. Lalu yang kedua, setiap membernya, setiap batang-batangnya itu dihubungkan dengan smooth pins, dengan pin yang halus, pin yang tidak ada gesekan di dalamnya. Oke, smooth pins. Arti dari smooth pin itu apa? Itu berarti di tiap pin yang ada tidak akan ada momen di sana. Ya, tidak akan ada momen di setiap pin tersebut karena tidak ada gesekan di sana. Jadi hanya akan ada gaya yang bertemu di satu titik di pin tersebut. Okay, so basically these are the two main assumptions that we will use when we analyze trust. Okay, all loadings are applied at joints, and the members are joined together by smooth pins. The meaning by smooth pin here is there is no friction in the pins. Okay, there is no friction happening at the pins. Okay, what does it mean? It means that at the pins there will be no moment at the pin. So basically, it will be only force happening at the pin, like that. Only force only happening at the pin. Okay. And when we talk about trust, okay, we will only talk about two force member only. Okay, when we talk about trust structures, all the member are two force members. So basically, that's the way to differentiate between trust structure and frame or machine. Okay, frame and machine, it's a different kind of animal. Why? Because all the members, not necessarily all the members are two force members, but when we talk about trust, all the member in the trust, we can consider that as two force member. Jadi ini perbedaan utama antara trust dengan frame dan juga mesin, ya, yang nanti akan kita bahas setelah trust selesai. Oke, trust itu semua member, ya, semua batang-batang yang ada di dalam trustnya itu bisa kita anggap sebagai batang dua gaya. Itu adalah definisi dari trust. Ya, saat salah satu anggota, salah satu member atau salah satu batangnya itu bukan batang dua gaya, berarti struktur yang kita tinjau bukan lagi truss. Seperti itu. Jadi saat kita membicarakan batang dua gaya, itu bisa dilihat ya, kalau tidak tarik, ya tekan. Jadi batangnya, setiap batang yang ada di truss, di struktur truss, itu kalau tidak mengalami beban tarik, ya mengalami beban tekan. Opsinya hanya itu aja. Oke, tidak ada beban-beban lainnya, tidak ada momen di sana. Bebannya, batangnya tidak mengalami momen. Dan batangnya juga tidak mengalami beban, beban tegak lurus terhadap batangnya. Jadi hanya tegak, hanya tarik atau tekan. Jadi arah kerja gayanya pasti searah dengan batangnya. Karena either tarik atau tekan. Ya. So when we talk about truss, okay, the one that I talked about before, right? All the member in the truss structure is always two force member. And what is so special about two force member? In the two force member, all the member there, all the beam there, is either under tension or under compression. So the loading that will be happening at the member is either tension or compression. So the loading there will be tension force or compression force. And what is so special about that, because it's only either under tension or under compression, okay, the line of action of the force in the member, in each member, is always the same, in the same direction as the member itself. So the force line of action is always the same as the alignment of the member itself. Jadi arah garis kerja gayanya selalu sama dengan arah dari batangnya itu sendiri. Okay. And when we talk about smooth pins, right, all the things that is like this, okay, we will consider this as a smooth pins. So we assume all the joint are smooth pins. Although in reality it's not smooth pins, but to simplify the case, we will always assume it as a smooth pins for statics class. Okay, for only statics class, yes, all the joint, right, we will consider as smooth pins. Okay, this is simple example of a simple truss. Yeah. Okay, you can see, right? Whenever we talk about a truss structure, most of the time there will be a constraint there. Sometimes and most of the time, one end will be pin joint and the other end will be ball joint like that, but not necessarily always like that. Okay, but this is the example. Okay, this is another example. Most of the time, the load it's under load like that, and for sure, when we talk about the load, right, the load will can be only given at the end of the member, at both ends of the member. So either this end or this end for the member AZ, this end or this end for member CB, and this end for member AB. So when we talk about truss structure, it is not possible for us to give the load in the middle of the member. Okay, the rule is like that. If that's the case, then this particular member is not a two-force member anymore, and we cannot consider this structure as truss structure anymore. So when we talk about truss structures, the load is always happening at both ends. Okay, only at both ends. The same as this one as well. We can still consider this one as a truss structures because the load is only happening at both ends. Oke, jadi saat kita membicarakan terkait dengan struktur truss, ya, salah satu aturan utamanya adalah beban yang terjadi hanya bisa terjadi di ujung-ujung batangnya saja. Ya, hanya bisa terjadi di ujung-ujung batangnya saja, di ujung-ujung membernya saja. Tidak bisa gayanya kita berikan di tengah-tengah member. Tidak bisa gayanya kita berikan di tengah-tengah batang. Kalau ada gaya di tengah-tengah batang seperti itu, batang CB ini misalnya dalam kasus ini, itu bukan lagi batang dua gaya. Sehingga si struktur keseluruhannya bukan lagi struktur truss lagi. Karena definisi dari struktur truss itu, semua batangnya, semua membernya harus merupakan batang dua gaya. Oke. Nah, yang kasus kanan ini juga termasuk kasus kasus truss juga, karena semua pembebanan hanya diberikan di ujung-ujungnya saja, dan semua batangnya adalah batang dua gaya. Gitu ya. Nah, the next thing that we want to discuss about is how can we analyze the force which is happening, at each member. Okay. The first method that you have to master is join method. Okay, by using this join method, we can analyze the force which is happening at each member. Okay, how can we analyze it? Okay, there are several ways to analyze it. Okay, we can try to analyze, because as you can see, right, this structure ABC is actually a rigid structure, and we can try to analyze the external forces which is happening to this particular triangle first. So you can try to solve for AX, AY, CY. Okay, if we try to draw the free body diagram like that, okay, there will be like this, right? 500 if we try to implement the equilibrium, the things that we learn in the equilibrium, right? This one is 500 Newton. Beside that, there will be AY, AX, and CY here, because C is a ball joint. Okay, roller. There is a roller at C. At A is a pin joint, so there is AY and AX at A. Okay, so we can try to solve for AY, AX, CY first to solve this. Okay, then after that we can try to solve for each joint. But sometimes it is not necessary for us to solve for the external force. For this case, it's one of those conditions. Why? Because we can try to take a look at the joint B there. So basically, when we talk about joint methods, right? We are talking about we are trying to list. Okay, we are trying to analyze all the forces which is happening at that particular joint. So for example, I want to analyze joint B. Okay, what forces which is happening at joint B? Muhammad Zahid. Hello, Muhammad Zahid.
Yes, sir.
What forces which is happening at joint B? Say it.
Joint B.
Joint B. Okay. Actually, the 500 Newton is there, right? Zahid?
Yes. Yes.
What else? What else is happening at joint B?
Tension, I think.
Not necessarily tension, but beside the 500 Newtons at which is happening at joint B as well, there is a member AB connecting to joint B, right?
Yes.
At one end, and member BC connecting to joint B at one end as well. Correct, right?
Yes.
And remember just now, when we talk about truss, each member is two force member, right?
Yes. Yes.
Yeah. So it's either under tension or under compression. So when we talk about each member, it can be under tension or under compression, right? We can also talk about what is happening at the joint, right? Sahid, correct, right? Sahid. So when we take a look at joint B, okay, there is a 500 Newtons going to the right. Beside that, if I want to include there the force due to member AB, okay, then I know that the force will be in this direction, right? Because the
Yes.
member AB is going in that direction, right? Correct or not, Said?
Yes. Yeah, correct.
And then if I want to include the force due to member BC, the force most likely will be in this direction, right? Because I know
Yes.
the member BC is going in that direction. Okay. Now, if I want the next thing that I can do in order to solve for the force happening at the joint B, then I can draw the force due to member AB and member BC. Okay. Now, in this example, there is a tension. AB is under tension, BC under compression. But the one that I will teach you guys is always assume each member that is joining at particular joint is under tension. So if it's under tension, then it will be like this for joint for force due to AB. And it will be like this for the force due to member BC. Correct, right? Said? Because both
Correct.
are tension, right? So
Yes.
if member AB is under tension, so actually because it's action and reaction, the member AB will pulling the joint B, right?
Oh, yes.
Okay, so let's try to draw member AB. If it's this one is member AB, this is the force. This one is A, this one is B, right? This is the force because of member AB. And if I want to draw member BC, okay, 45 degrees. If it's under tension, it's supposed to be like this. This one is BC. But remember, at joint B, it will be action and reaction, right? So when we take a look at the member AB, okay, at point B there, okay, joint B will pulling member AB there. That's why the force is going up there. Okay, if we take a look at member BC, okay, at joint B, okay, joint B there will be pulling member BC over there. That's why it's going to the top left. But on the other hand, okay, okay, when we take a look at the free body diagram of joint B here, okay, when we take a look at the free body diagram of joint B there, member AB will be pulling joint B, so it's going down there, and member BC will be pulling as well joint B, so it will be going to the bottom right there. Okay, so it's action and reaction. Okay, do you get it, Sahid?
Yes, sir.
Jadi ini mungkin saya jelaskan lagi ulang dalam bahasa Indonesia ya. Saat kita menganalisis dengan menggunakan joint method, kadang-kadang kita bisa menyelesaikan terlebih dahulu gaya-gaya yang bekerja pada supportnya ya, pada titik A dan titik C, kita cari AX, AY, CY, seperti itu. Tetapi kadang-kadang juga tidak perlu melakukan itu. Jadi kita bisa langsung cek di join-nya saja dengan menggunakan join method. Nah, join method itu seperti apa? Yang kita perlu lakukan adalah kita coba melis semua gaya-gaya yang terjadi pada join tersebut. Ya, pada titik B, join B, itu kita bisa lihat bahwa yang gaya yang bekerja di sana adalah gaya 500 Newton akibat 500 Newton ke kanan ini, plus ada BA, ya, batang AB itu ada di situ, dan juga gaya dari batang BC. Ya, batang AB dan juga batang BC. Itu akan memberikan juga gaya ke join B. Nah, ini saya asumsikan dulu, semua gaya akibat member yang ada di sana di titik B itu tarik. Saya asumsikan. Nah, kalau tarik, kita melihat join B, terus member AB itu memberikan gaya tarik, artinya member AB itu menarik titik B. Ya, menarik titik B. Jadi sehingga gayanya arahnya ke bawah seperti itu. Dan BC, batang BC memberikan gaya tarik ke join B, sehingga arahnya ke kanan bawah. Karena dia menarik ya, si batang tersebut menarik titik B. Nah, di lain pihak, kalau kita melihat batangnya, diagram benda bebas batangnya, itu kebalikannya. Oke, kalau kita melihat diagram benda bebas dari, ini yang bagian ini kalian nggak usah lihat dulu ya. Malah nanti membingungkan. Oke, kalau kita lihat batang AB misalkan ya, kalau kita lihat batang AB ya, kalau kita lihat batang AB itu di titik B, join B menarik batang AB sehingga ada gaya ke atas di sana. Ingat ya, aksi reaksi, selalu aksi reaksi. Oke, sama juga di batang BC, di titik B itu join B itu menarik batang BC di titik B sehingga gayanya arahnya ke kiri atas. Seperti itu. Okay. Until this point, how to draw the free body diagram at the joint and the member. Okay. Anyone here want to ask question? Okay. When we talk about a member, when we talk about the member, it's either under tension or under compression. But in order to simplify the case, always assume first that each member is under tension. So maybe some of you will ask that. So, Pak, if in reality it will be it is under compression, then what will happen? It's okay if we assume it under all the member under tension. So, if the value in particular member is negative, it means at that particular member it will be under compression. That's why it's simple. It's much simple if we assume all the members is under tension first. Later, when the value is negative, so that particular member will be it's supposed to be under compression, like that. Anyone want to ask question here? Ya, untuk mensimplifikasi kasusnya, itu lebih enak kalau kita mengasumsikan bahwa setiap member, setiap batang itu mengalami beban tarik. Ya, seperti yang saya gambarkan sekarang. Nah, kalau misalnya kondisinya nanti ternyata kondisi kenyataannya adalah dia mengalami beban tekan, itu apa yang akan terjadi? Nilainya akan negatif. Jadi nanti kalau ada kita mengasumsikan semua member, semua batang itu tarik, ya, mengalami beban tarik, tiba-tiba ada satu batang yang mengalami beban, nilainya negatif, ya, itu artinya batang tersebut itu mengalami tekan. Seperti itu. Anyone want to ask question here? Hasil Herlambang, apakah dipahami?
Paham, Pak. Sakia, apakah dipahami Sakia? Halo Sakia?
Ya, Pak.
Apakah dipahami?
Paham, Pak.
Sip. Oke, Lilo, Handaru.
Yes, sir.
Do you understand?
Yeah, Pak.
Okay, good. Okay, now let's try to solve this then. Okay, we already draw the free body diagram at joint B, and you can see there the FAB is tension, FBC we assume it tension as well, and we have 500 newtons going to the right. Okay, and remember all the forces there is happening at joint B, so everything is happening at the same point. Okay, now I want to ask Lilo again. Okay, Lilo, in order to solve for this particular free body diagram, Lilo, to solve for the value of FAB and FBC, Lilo, okay, what equation that we can use, Lilo? Remember, In order to solve for this, we always return back to the equilibrium equation.
Here we can separate FBC into factors and then use.
Yeah. Later, yes, you can do that. But I mean, you have to list out first the equation that we can use, equilibrium equation that we can use to solve for this.
Is sigma fx equals 0.
Okay, sigma fx equal to 0. What else?
Sigma fy.
Yeah,
Equals
sigma
to 0.
fy equal to 0. Can we use sigma moment here, Lilo?
No,
all the forces
because
are happening at one joint, right? So we cannot, yes, correct. We cannot use sigma moment because all the forces there happening at the same point. So there will be no use of using sigma moment. So we only have two equations. And now, Lilo, how many unknowns that we have in that particular joint?
one.
How many unknowns that we have in that particular joint, joint B?
Two force.
Yeah, FAB and FBC. We have two unknowns, FAB and FEG, and we have two equations, sigma fx equal to 0 and sigma fy equal to 0. In that case, Lilo, will we be able to solve it?
Yes, of course.
Oh, yes, correct. Now, Lilo, help me to solve this then. Try to implement sigma fx equal to 0 first.
Okay, on the x-axis we have FBC.
This one is 45 degrees, right? I believe.
Yeah.
So
FBC cos 45
cos
plus 500
so
equals 0.
going right is positive, plus 500 Newton. What else?
That's it, sir.
That's it. Okay, equal to 0. Okay, in this case, will we be able to solve for FBC?
Yeah.
Yeah.
So
what is the value of FBC?
FBC is 500 divided by cos 45.
Are you sure 500?
Minus 500.
Minus 500. Don't forget the minus. It's very important. Minus 500 divided by cos 45 degrees. What is the value in decimal?
It's 707.1.
707.1 Newton, like this.
Yeah.
Okay, minus, remember. Okay, just now I talk about it, right? If the value is minus, what does it mean, Below?
It goes to the opposite direction of the assumption.
Yeah, we first assume it as tension, right? Under tension, FBC under tension. So the BC, the member BC, we assume it as under tension. So in reality, okay, it's supposed to be under what?
Compression.
It's supposed to be under compression with the value of the compressive force is 707.1 Newton, like that. Okay. You get it, Lilo?
Yeah, sir.
Now, what else that we can solve here?
We can find FAB with sigma Fy equals 0.
Okay, sigma Fy equal to 0. So what do you have there?
We have FBC sine 45.
Okay.
Minus
FBC sine 45 degrees minus or plus?
Plus.
Plus. So going down is positive, plus
FAB
equal to 0. Okay, FBC, we know the values, right?
Yeah.
Okay, so what you got there?
Okay, wait, sir. So it's minus FAB divided by sin 45.
Minus FAB. No, I think it's better for you because we want to find FAB, right? So.
Oh yeah, sorry.
So FAB equal to minus FBC sine 45 degrees like that, right?
Yeah.
Okay. What is the value of FBC?
FBC is 707.1.
Don't forget about minus.
Oh yeah, minus.
So here it's minus 707.1 Newton sine 45 degrees. Because just now we use the original direction. We use the original assumption, right? FAB is going down, FBC is going to the bottom right. Okay, but remember the FBC has negative value, right? So
Yeah.
just now, in order to solve this, we use the free body diagram over there. So after we modify it, it becomes like this. And this, right? Because the value of FBC is negative, correct, right, Lilo?
Correct.
Yeah. So FAB, the value is positive. So what is the value of FAB there?
It's 500 Newton.
Positive. What does it mean there?
It means it's
Under tension or compression?
under tension because it's positive.
Yes, correct. So in order to see, in order to make it clear, okay. So you can just put it like this: 500 Newton tension. This one is 707.1 Newton compression. Like that. Okay, Lilo?
Yes, sir.
Okay, so we're able to solve for FAB and FBC. Okay, good. Thank you very much, Lilo. Okay, Lilo, would you mind to point somebody else here to help me to solve for a member AC now? Because we have 3 members, right? Here, member AB, BC, and AC. We already solved for FAB. We have already solved as well for FBC, but we haven't solved for FAC. Do you want? Who do you want to do it for me, Lilo?
Or maybe Marcellus Mario.
Marcellus Mario.
Yes.
Okay, Marcellus Mario. Now we are left with AC Mario. We solved for FAB, we solved for FBC, but we haven't got the FAC yet. How to solve for FAC, Mario?
Draw the free body diagram of C.
Okay, draw the free body diagram of C. Okay, at C, if this one is C like that. Okay, this one is C. Okay, what forces is happening at point at joint C, Mario?
FCB.
FCB. Okay, what else?
FCA.
FCE. Yes, from member AC. What else? How about from the roller joint, Mario?
Reaction force C.
Yes. CX. Are you sure we have CX there? Remember, it's a roller joint.
CY.
CY, correct. So we have FBC, we have FEC, we have CY. Okay. Just now, in the previous free body diagram, we assume that FBC is tension. Okay. But in reality, in our calculation, FBC is already found. We already found out that FBC is 707.1 Newton, but compression. Okay. So now, in order to draw the 707.1 Newton compression, which direction that I supposed to draw for FBC? It's supposed to be going to the, because the direction of FBC is 45 degrees, right? So the line of action must be like this. But it's supposed to be going to the top left or the top right. Hello, Mario?
Top left.
Top,
Left.
top left. Top left like this. Hey, sorry. If it's top left like this, means that we assume it as tension, right? But remember, it's 707, but it's compression, you know. Hello, Mario? I want to draw the real direction right now, not the assumption like before. This one is assumption, right? But we already found out that it's 707.1 Newton and it's compression. Hello, Mario?
So down, right?
Yeah, correct. It's supposed to be going down, right? Because it's compression. Because the reality is under compression. I don't want to assume it anymore because I already know, right? So it's supposed to be going like this. This one is FBC. So if I want to draw the member BC, okay, this is what exactly happening at member BC. It will be under compression. Okay, Mario? Because we already know from the previous calculation, so now we don't have to assume for FBC. Correct, right, Mario?
Yes.
Now, the next one is what else that we have there? FAC. Where we're supposed to put the FAC is supposed to be horizontal, right? Because the line of action is like this. Okay. Do you know the value of FAC, Mario?
No.
No. In that case, if we don't have the value yet, always assume it as tension. Okay, Mario?
Okay.
If it's tension, it's supposed to be going left or right?
Left.
Left, correct? Left, like this. This is under tension. FAC. So if we draw the member AC, okay, it's supposed to be like this. Okay, Mario? It's going to the left. Okay, FAC is going to the left. Okay, what else do we have there, Mario, beside FBC and FAC?
CY.
Hmm?
CY.
CY, correct. Okay, you can assume anything for CY. Okay, I assume it is going up like this. Okay, the angle here is 45 degrees. Okay, FBC, we already know the value, 707.1 Newton. What equation that we can use here, Mario? What equilibrium equation that we can use here to solve for the unknowns, Mario?
Sigma Fy.
Okay, sigma Fy equal to 0 and
Sigma Fx is equal to 0.
sigma Fx equal to 0. Only these two. Okay. Remember, okay, everyone, because for joint methods, we analyze the free body diagram of each joint, right? Each joint, we analyze the free body diagram of each joint. Then, for each joint, we will have two equations. Normally, for each joint, we will have two equations. Sigma Fx equal to 0 and sigma Fy equal to 0. There will be no sigma moment equal to 0. There will be no sigma moment equal to 0. Why? Because all the forces are happening at the same point. So there will be no use of sigma moment. Okay. Now, Mario, which one that we have to solve first, Mario? CY or FAC?
CY.
Yeah, actually, you can do both, right? It's up to you. Okay, CY. In order to solve for CY, we use sigma Fy equal to 0 or sigma Fx equal to 0?
Sigma Fy.
Sigma Fy equal to 0. So, Can you elaborate for the sigma Fy equal to 0, Mario? What forces that we have in the y direction there?
707.1 sine 45.
Correct. 707.1 Newton. What else?
Sin 45.
Sin 45. What else?
Minus cy.
Minus cy, correct. Minus, yeah. Minus cy equal to 0, like this, right?
Yes.
Yeah. So going down is positive. It's okay. It's up to you. You can choose going down or going up is positive, but this one is correct. From this, can we solve for cy, Mario?
Yes.
Okay, cy is equal to 707.1 Newton sin 45 degrees. So what is the value of cy?
500.
Correct, 500 Newton. Now, sigma fx equal to 0. Will you mind to elaborate for this?
707.1 cos 45.
Cos 45 degrees.
Minus FAC.
Correct, minus FAC equal to 0. So from this, FAC is equal to 707.1 Newton cos 45 degrees, which is the same to 500 Newton. Like this, right, Mario?
Yes.
Okay. So in that case, FAC there is 500 Newton tension or compression, Mario?
Tension.
Tension, because it's positive, so it's tension, right? Okay, so that's it. Okay? We already solved for all the members forces. FAB is 500 Newton tension. FBC is 7.1 Newton compression, and FAC is 500 Newton tension. We know as well that the reaction force at C is Cy equal to 500 Newton going up, but we haven't solved yet for AX and AY. If it's not us, then we don't have to solve it. But if it's us, then we can solve it by solving the joint A. By solving joint A, you will be able to solve for AY and AX. Okay. So basically, I will try to repeat again of what things that we have done up until now. Okay. Mungkin saya jelaskan dulu dalam bahasa Indonesia ya. Jadi di sini kita sudah menyelesaikan ya gaya-gaya yang terjadi pada setiap member. AB itu 500 Newton gayanya, tarik. FBC itu 707,1 Newton tekan. AC itu FAC 500 Newton tarik. Selain itu kita juga sudah menemukan nilai reaksi di titik C, CY, itu 500 Newton ke arah atas. AX dan AY kita belum temukan. Kalau tidak ditanya, kita tidak perlu jawab. Kita tidak perlu cari. Tetapi kalau misalkan ditanya, kita bisa menyelesaikan nilai AX dan AY itu dengan cara menyelesaikan free body diagram di join A. Kalau kalian menyelesaikan free body diagram di join A, kalian bisa mendapatkan AX dan AY. Oke. Nah, ini saya coba rangkum ya terkait dengan apa yang kita kita sudah lakukan untuk menyelesaikan kasus Truss ini. Truss yang paling sederhana ini karena segitiga ya. Itu urut-urutannya bagaimana? Step by step-nya bagaimana? So, if I can summarize on how can we solve for the Truss problem in order to know all the force happening at each member, then this is it. Okay, you can see we can try to determine the force direction by inspection. But I don't like it because some people can do it intuitively because they have a good engineering sense, but some other cannot. So what I suggest you to do is the number 2. Always assume the unknown member forces acting on the joint free body diagram to be in tension. Like what I did just now. When I don't know the value which is happening at a particular member, I always assume tension first. Like FAB and FBC here. Okay, FAB in reality, yes, it's under tension, 500 Newton. FBC, unfortunately, is under compression, 797. That's why the result is negative. But it's okay, because it's negative. We know that the direction is the opposite of what I assumed at the beginning. So it's supposed to be under compression. Then in the next free body diagram, I replace the direction. I change the direction for FBC. Because now I know the FBC is under compression in the in this particular free body diagram. Okay, the next free body diagram, the free body diagram for joint C, instead of assuming it under tension again, I assume it as not assume, because we know already that it's under compression. I draw it as compression there. Under compression, the FBC is compression. Compressive force of 7.1 Newton. That's why the direction is, instead of going to the top left, it's going to the bottom right, because it's under compression. But on the other hand, AC there, I don't know the value yet. That's why I assume it as under tension. Because as it's stated here, if you don't know the value, if you don't know the direction of the member of the force which is happening at the member, always assume that it's under tension. Okay, that's the easiest way to do it. Okay, assume everything under tension, all the member under tension, all the members under tension. Then if it's negative, then it's under compression. If it's positive, then it's correct, it's under tension. Okay, next is the procedure of the analysis. It's like this. Okay, sometimes if it's necessary, in the previous case it's not necessary. Okay, if necessary, sometimes we have to solve the external forces at the support first, if necessary. Okay, and then the next one is to draw the free body diagram of the joint, like what I did here, because solving for the external forces happening at A and C because of the joint there is not, because of the constraint there, is not necessary. That's why I try to solve it directly from joint B. Okay, from joint B, I try to solve it directly from joint B. So I draw the free body diagram of joint B, like that. Okay. Then, after drawing the free body diagram of a joint, use one of the two methods described above for establishing the sense of the unknown force. Okay, in this case, we use the second method. Just now, we assume that at joint B, AB and BC is under tension, and 500 Newton is because it's known already, it's going to the right. Okay, then after that, we can also as well orient the X and Y axis, but in this case, we don't need to do that because X-axis is already horizontal and Y-axis is already vertical. But sometimes it will be easier for us to calculate it if we change the direction of the X and Y axis. Okay. Then apply equilibrium on the joint. Remember, when we apply the equilibrium here, we will only have two equations: sigma fx equal to 0 and sigma fy equal to 0. We will not have sigma moment equal to 0. Why? because all the forces are happening at one particular point. So there will be no sigma moment equal to 0. We will only have two equilibrium equations. Because we only have two equilibrium equations, at each joint, we can only solve for two unknowns. Like this, right? Oh, joint B, we have two unknowns, FAB and FBC. We can solve it. Joint C, we can. There are two unknowns as well, FAC and CY. We can solve it. Okay. So don't choose the joint which has more than more than two unknowns. We can only solve for two unknowns for each joint. You get it, guys? Okay. Up until this point, anyone want to ask question? Anyone want to ask question for this? Not? Is it clear enough? Okay. I believe maybe because it's too theoretical, it's better for us to try to solve for this particular problem together. Okay. Sebentar ya, saya coba lihat dulu. Reinhard, apakah dipahami Reinhard? Reinhard Rema. Halo?
Halo, Pak.
Paham tidak?
Paham, Pak.
Sip. Kalau sebentar. Hilmi dan juga Raka Wicaksono juga di Muhammad Hilmi Hakim. Apakah dipahami sampai titik ini?
Bisa dipahami.
Oke. Oke, kita lanjutkan ya. Ini coba satu contoh soal dulu sebelum saya membahas terkait dengan zero force factor. Ya. So I think it's better for us to go for the problem example here in this particular case. Then after that we can go for the zero force member, discussion about the zero force member. Okay. The question here is okay. The question here is we have to find out all the members, all the forces which is happening at each member, like this. Okay. My first question is, do we need to solve for the external load happening at the constraint or not? Marcia Virginia. Halo Marcia. Apakah kita do we need to solve for the the external load happening here and here or not? Marcia? Hello, Marcia? Can you speak? Yeah. Do we need to solve for that one first, or we can go we can use join method directly in this case?
I think we can solve the roller and the pin one, sir. First,
Sorry, we can solve for the what?
the point B1, sir. The first one.
The first one is this one, you mean?
Yes.
Do we need to solve for the external force first or not? This and this.
I guess.
Actually, the answer is not necessarily, Marsha. Okay, let's take a look together. Okay, Marsha. Okay, remember, just now I talk about when I talk about it. Okay, each join method, it's join. Okay, at each join we can solve for two unknowns. Okay, in order to use join method to solve for all the member, what we can do is we can try to take a look at the join first. Okay, first try to take a look at join A. How many unknowns that we have there, Marsha?
Join A, we have the X and Y.
X, A, Y. How about from the member?
Also the AD one.
AD. How about AB? AB as well.
Yes.
AB as well. So we have how many unknowns there? 4, right?
We have 4.
Okay, now take a look at join B. How many unknowns that we have there?
The AB,
AB,
BD,
BD,
BC,
BC,
and
BY. Correct. So 4 unknowns as well, right? In total. Now, join D. How about join D?
Join D, we have the AD,
AD,
DB, and DC.
DC. So we have 3. Now, last one, C. Join C.
CD and CB.
That's all, right? Only 2 unknowns. So after we analyzing it like this, okay, each join, this is the number of unknowns that we have at each join. Okay, do we have join which has only 2 unknowns, Marcia? Yeah, this one, right? Which means we can solve for that one first, Marcia. Okay.
Yes.
So the answer is, for this particular problem, it is not necessarily for us to solve for AY, AX, and BY first. We can go directly from join C, Marsha. Okay.
Yes, sir.
Okay. Now, I want you to help me to solve for join C, Marsha. Okay, it is known that the angle here is 45 degrees. Okay, and this one as well is 45 degrees. Because the triangle here and the triangle here are the same. So the angle there must be the same as well. Now, I want you to draw the free body diagram of joint C, Marsha.
So it'll be from point C, it will go like there will be force downward 5,000 Newton.
5,000, correct, 5,000 down.
And then 45 degree to the bottom left. But just like the arrow, no need to draw the full one.
So
or
it's
BC.
Like, okay, like this. You want it to be bottom left or top right? Do we know the value of FBC or not? No, right?
No.
No. In that case, always assume as tension or compression.
Can be either.
No. Yep, it's supposed to be can be either. Yeah. It's you can do it for either of those. But based on what we discussed before, in order to simplify the calculation, always assume it to be tension. If you don't know the value yet, okay, Marja?
Okay.
So if it's if we assume it's under tension, it's supposed to be going to the bottom left or top right?
Upright.
Hey, tension.
Tension.
Tension means the member BC is pulling the joint C, right?
So yeah, it's bottom left.
Bottom left, correct. So that's the way to imagine it. So this one is F, BC. So the last one, how about DC then?
DC, since it's also unknown, we can assume it's tension also.
Yeah, tension is supposed to be going to the left or to the right?
To the left.
Left. Okay, going to the left. F, C, D. Okay, like that. So that's it. This is 45 degrees. Okay, now how many equations that we can use to solve for these two unknowns?
The fx, sigma fx, sigma fy.
Sigma fx equal to 0 and sigma fy equal to 0. Okay, for sigma fx, would you mind to elaborate for that? Sigma fx equal to 0?
Sigma fx will be FCD.
FCD. What else?
And FBC sine 45.
Plus
FBC.
or minus? It's going to the same direction. It's going to the left. So if say FCD is positive, then
positive.
FBC is positive as well. Positive FBC cos
45
is equal to
0.
Okay. We have two unknowns there, so we will not be able to solve for fx, sigma fx equal to 0 yet. Okay. Now try to elaborate for the sigma fy equal to 0.
It'll be the 5,000 Newton.
Okay, 5,000 Newton. What else?
Plus F sine cos 45.
FBC.
FBC sine 45. I'm sorry.
Okay, equal to 0. Okay, from this, we will be able to find out that FBC is equal to what?
Give me 1 second, sir.
Now, FBC, yeah. Try to solve for this. You can solve for that, right? FBC, 5,000 Newton plus FBC sine 45 degrees equal to 0. In this case, it's only one unknown there, right? In one equation. So we can solve for FBC, right? So, would you mind to solve for FBC then?
Okay, sir.
So FBC is supposed to be equal to what?
5,000. Negative 5,000.
5,000
over sine 45.
Sine 45 degrees. So the result is supposed to be
7,698.84.
7,000. So wait. Are you sure? Cos 45 sin 45 is what? Oh yeah, correct. 7,000 what? Sorry.
7,698.84.
7,698.84. 0.84. Newton. Okay. So it's minus, right? Wait a minute. Let me check. $5,000 divided by cos sin 45. Why my calculator is not like that? Sin 45. Okay. Wait a minute, 5,000 divided by sin 45. Are you sure? My calculation here is supposed to be 7,071.
I'm sorry, I think
Correct, right? 7,071, right? Instead of 7,600. Hello, Marcia?
I think so, sir. But I think my calculator's been bugging with the sign. We might have somehow switch it up into the radian, sir. I think.
Yep. It's better for you to fix it before the quiz and exam, okay? Because if not, everything will be mixed up for your case. Okay?
Yes, sir.
Okay. Minus 7,071 Newton. Okay. It means that it's under compression, so it's supposed to be 7,071 Newton compression, right?
Yes.
Okay, FBC is solved. Then can you solve for FCD? Hello, Marja. Can you solve for
Sir.
FCD, Marja?
Can.
Just use this equation, right?
Yes.
This one. Okay. Would you mind to solve for FCD then?
Yes, sir.
So FCD plus FBC, which is known. Okay. The FBC is minus 7,071 Newton. Cos 45 degrees equal to 0, right? Like this, right, Marja?
Yes, sir.
Okay, so FCD is equal to 7,071 cos 45. So it's supposed to be around 5,000, right?
Yes, it's 4,999.
Yeah. Okay. So basically, because just now we round it up, they round it down, then this one is supposed to be close to 5,000. Okay.
Yes.
So it's supposed to be under tension, right? FCD is under tension 5,000.
Yes.
Now, using the known value here, if we now take a look at joint D, how many unknowns that we have there?
We have 2.
2, right? Because FCD is already known. So now it becomes 2. So now we can solve for joint D. But if we take a look at joint B, there, the number of unknown is still 3, right?
Yes.
Because we only solve for CB. So the number of unknowns is now 3 there. So we cannot solve for joint B yet, but we can solve for joint D, right, Masha?
Yes, we can.
Okay, so that's the thing for a joint method. After you solve for the joint where the number of unknowns is 2, then try to take a look at the other joint. After you solve for the previous joint, try to take a look at another joint, which now the number of unknowns is becoming 2. So in this case, then we can take a look at joint D, right?
Yes.
Masha? From joint D, we will be able to solve for FBD and FAD, correct, right? Masha?
Pardon, sir?
From joint D, we can solve for FBD and FAD, right?
Yes.
We can solve for FBD and FAD. Then, because we already solved for those two, now joint B having 2 unknowns right now, right? After you solve for joint D. Joint B
Yes.
now becoming 2 unknowns, only 2 unknowns, FAB and BY. Then you can solve for that joint B. And the last one is if you need to find out for the AY and AX, you can solve for joint A. Do you get it, Marcia?
Yes, I understand,
So
sir.
method of join for everyone here. Okay, method of join. We can try to solve it one by one. First, try to find a join which has only 2 unknowns. Then, after you solving for that, try to find another join, okay, which now having 2 unknowns. Then solve for that. After you solve for that, try to find another join that now is having 2 unknowns. Solve for that until all the joins are solved. Okay. Until this point, anyone want to ask questions? Okay, please. If you have any questions, you can just turn on your mic and ask me directly. Okay. Actually, we can just practice for the join method. But there are several other examples here. But I believe you can try to practice it by yourself as well to solve for this. Okay. So basically, that's it. Okay. In order to solve the forces happening at each member using join method, we can try to analyze each join one by one. Start with the join which has only 2 unknowns. Then we go for the next join which has 2 unknowns. Then we go for another join that has 2 unknowns. Okay, now, Malsa, please point out one of your friend to help me to solve for this one, Marsha. Another problem example. After that, I will explain about the zero force member. Hello, Marsha.
Maybe Phoebe, sir.
Phoebe. Okay. Phoebe. Hello, Phoebe.
Yes, sir.
Okay, Phoebe. Now, I don't want you to help me to calculate for the forces which is happening at each member, but I want you to show me the sequence to solve for this particular problem.
I think we can start with point D.
Point D, because at point D, they only have 2 unknowns, right?
Yes.
FCD and FAD. So it has 2 unknowns. So you can solve for this. Okay. And after that?
And then we move to point C.
Okay, then we move to point C. So this one is the first step. Then we move to point C. This is the second step. After we solve for FCD and FAD, at point C right now, we only have 2 unknowns, which is FCB and FBC and FAC. Correct, right, Phoebe?
Yes.
Yeah. So we can solve for join C right now. So that's the second step. Then after that, which one?
We can go
let me check. Okay?
or B.
I will give it like this. Okay. So now using the 2 join, the one that I picked just now, okay, is the solve. Get it? I will repeat again. Okay, using the first join D, I can solve for this and this. Now using the second join C, okay, I can solve for this and this. Okay, now take a look there, Phoebe. Which one that we can go for after that?
A.
A. B cannot. You cannot go to B yet because at B we have BX and BY, so we have 3 right now. Okay, but at A we have AY and FAB, right?
Yes.
So we can solve for this particular join. So this one is number 2, this one is number 3. Okay, after that, then we have this. And this one. AX. Sorry, X. Yeah. Okay, Phoebe? Correct,
Yes,
right?
sir.
Yeah.
Yep.
So basically it's like that. When we talk about join method, we can determine the sequence by looking at the number of unknowns. Oke, jadi ini saya coba ulang penjelasannya dalam bahasa Indonesia ya. Jadi saat kita menggunakan join method, kita itu bisa melihat urut-urutannya, bagaimana kita menyelesaikan ini dengan melihat jumlah unknowns-nya. Kita lihat dulu secara keseluruhan. Oh, di sini kondisi awal titik C itu ada 3 unknowns. Ya. 1, 2, 3 unknowns. Titik B ada 1, 2, BXBY. Jadi ada 4 unknowns di titik B, kondisi awal. Lalu titik A ada 1, 2, 3 plus AX. Jadi 4 unknowns juga di kondisi awal ya. Nah, kalau kita lihat di titik D itu ada 2 unknowns. Hanya ada 2 unknowns di kondisi awal. Jadi kita bisa analisis terlebih dahulu titik D. Oke, setelah kita analisis titik D dengan menggunakan, kita gambarkan diagram benda bebas titik D ya, seperti ini. Kita punya 300 LBF, lalu kita punya FAD, semuanya dianggap tarik semua ya. Lalu kita punya FCD, oke, kita bisa selesaikan FCD dan juga FAD. Dari sini kita bisa lihat bahwa sekarang setelah kita selesaikan join D, join C hanya ada tinggal 2 unknown saja. FCB dan juga FAC. Jadi kita bisa selesaikan join C. Oke, kita bisa selesaikan join C. Kita bisa dapatkan FBC dan juga FAC. Nah, setelah join C selesai, ini dapat, kita bisa selesaikan join B untuk bisa mendapatkan, join A ya, join A untuk bisa mendapatkan FAB dan juga AX. Seperti itu ya. Join B tadi belum bisa karena itu ada BXBY di sana. Seperti itu. Jadi urutannya seperti ini. 1 join D, 2 join C, 3 join A. Seperti itu. Zakiyah Nur Amani, apakah dipahami Zakiyah?
Iya, Pak.
Oke. Kamu masih ada yang bingung nggak Zakiyah? Terkait method of join ini? Halo, Zakiyah?
Iya, Pak.
Apakah masih ada yang bingung terkait dengan method of join ini?
Enggak sih, Pak.
Yakin ya?
Ntar saya review lagi.
Sip. Banyak latihan soal ya, Zakiyah?
Iya, Pak.
Sip. Oke. Jadi, so that's it. That's the method of join. Okay. Basically, the things that you have to do right now is to keep practicing because for statics, I always say that practice makes perfect. Practice makes perfect. So, if you want to have a better level of understanding and you know to how to solve it, whether you want to know whether your level is already going up and you can solve those difficult problem. Okay, try to practice more. Okay. Now, let's take a look at this particular problem. Okay. For this particular problem, before I go for the zero force member, I think I will call for, wait. Safran Ahmad. Hello, Safran.
Hello, sir. Yes.
Okay, Safran. For this particular problem, Safran, do we need to solve for the external force at joint A and joint G, or we can directly solve using joint methods?
I think we can use joint method.
Okay. Where are we supposed to start, Safran?
At
Remember, always start with the joint which only have two unknowns.
okay.
Which one, Safran?
Is it D or
Yes,
C?
correct. Is D. C. C, there are lots, Safran.
Okay, D.
There are a lot of members there. We cannot solve for C. Okay, but D, there are only two join, which there are two members which joining at a particular joint, right, Safran?
Yes, sir.
Okay, so we can solve for that. So if we try to solve for joint D, then this is joint D, and this is FCD, and this is FDE, right? Like this way, Safran?
Yes, sir.
Would you mind to solve it for me, Safran?
Okay.
What equation that we can use, Safran?
We can use the sigma fx and sigma fy.
X equal to 0 and sigma fy equal to 0. Try to use sigma fy first. What do you have?
Okay. For sigma fy, we have the FCD.
FCD cos this particular angle, right?
Yes, FCD cos
Cos theta, for example, theta like that equal to
equal to
0. 0, right?
yes, 0.
So what's the result of FCD?
FCD will be equal to cos theta.
How can it be? FCD multiplied by cos theta equal to 0, then FCD equal to cos theta. How come? Okay, how come? FCD is equal to 0 divided by cos theta. That's the correct one, right?
Yes,
Safran?
yes, sir.
So equal to what?
0.
0. Don't confuse yourself. Okay, Safran?
Okay, sir.
FCD is equal to 0. Now, using sigma fx, what you will get then?
We have the FDE and FCD sign.
Okay, FDE plus FCD sine theta equal to 0. FCD is equal to 0, right?
Yes.
FCD equal to 0. 0 multiplied by sine theta is equal to 0. Then FDE is equal to what?
0.
0 as well. So these two are 0.
Okay.
0 force member. Okay. Then after we know that those two are 0, would you mind to let me know which joint that we can go next?
We can try to find the C.
C? Are you sure C? This one is 1, 2, 3. Still 3. So, Fran, we cannot. We cannot go to joint C.
Okay, then E.
Why you try it one by one? Try to analyze it first, okay? Okay. This one we already know. This one we already know. So at joint C, we need to solve for this and this, right? So two unknowns. Can we solve for that? We can,
Yes.
right? Yeah. So we can go for joint E. Okay. We can go for joint E. Later, after you solve for joint E, if you solve for joint E, it will be like this, right? FCE P2 is 20 kilonewton. And then we have FDE 0, right? So we have one more is FEF. I don't draw FDE because FDE is equal to 0, right, Safran?
Yes, sir.
Now, using sigma, we have two equations as well, right here.
Yes.
Sigma Fx equal to 0 and sigma Fy equal to 0, right?
Yes.
Using sigma Fy equal to 0, what you will get, Safran?
We have FCE minus 20 kilonewton.
Yeah, equal to 0. So at the end, what you will have is Fc equal to 20 kilonewton, right?
Yes.
Okay. Using sigma Fx equal to 0, what you will get?
We have FEF equal to 0.
Yes, that's all. FEF is equal to 0. So this one is zero force member as well. Okay.
Okay, sir.
Now the next one is we can solve for this, right?
Yes.
Now joint C is left with 2 unknowns, so we can solve for that. Okay. After that, yeah. After that, we can solve for this one because it's left with 2 unknowns. Then after that, we can solve for this one because it's left with 2 unknowns. Do you get it, Safran?
Yes, sir.
So this one is number 1. This one is number 2. This one is number 3, 4, 5, like that. Okay, so step by step to solve for each member. Okay, Safran?
Okay, sir. Yes.
Okay. But the thing that I want to tell all of you guys in this particular problem is not that one. It's not the step. Yes, the step, I believe some of you already understand on how to solve for the steps. But the one that I want to talk about is just now based on our calculation. This one is 0. This one is 0. This one is 0. Correct, right, Jafran? Jafran? Those 3 are 0, right?
Yes, sir. Correct.
Okay, those 3 are 0. So if those 3 are 0, okay, sometimes we can try to determine the zero force member, those 3, okay, from the beginning of the analysis without even doing any calculation, just by using our sense to check whether some of the member are zero force member or not. That's the thing that I want to talk about. Jadi berdasarkan kalkulasi Zafran barusan, ya, yang utama di sini itu adalah member DE, member CD, dan member EF 3 itu adalah nilainya 0. Nah, yang penting ingin saya ungkapkan ke kalian itu adalah kadang-kadang bukan kadang-kadang, beberapa jenis zero force member, batang-batang yang gayanya 0, itu kita bisa analisis terlebih dahulu di awal dengan pengecekan visual untuk mengetahui apakah itu 0 atau tidak. Jadi kita tidak perlu hitung lagi. Jadi kita bisa langsung tahu bahwa oh ini zero force member. Seperti itu. Nah, itu yang akan saya bicarakan. Ya.
Saya boleh nanya.
Ya, silakan.
Kalau misalnya 0 tadi itu dia jadi compression atau tension?
Ya 0 nggak compression, nggak tension, 0.
Oke.
Kebayang nggak Hans? Ya.
Iya,
Kalau namanya 0 itu kita tidak ada tension, tidak ada compression. Dia tidak ada beban sama sekali di sana, Hans.
Oke, jadi dia free hanging gitu aja.
Betul, itu jadi kayak sesuatu yang memang akibat pembebanan yang ada itu tidak ada beban yang terjadi di sana. Gitu.
Tapi di dunia asli emang bisa 0?
Bisa 0, tetapi kondisinya sebaiknya ada beberapa kasus yang tidak bisa itu dilepas begitu saja, karena di pembebanan jenis lainnya bisa jadi itu muncul. Tidak 0 di sana. Kebayang nggak, Hans?
Oke, karena aku mikirnya kalau ada benda, ada beratnya, pasti ada force-nya.
Ya. Kalau misalkan kita melihat dari masanya dia sendiri, ya pasti akan ada beban dari dia sendiri ya. Tetapi yang lebih penting dari itu bukan itu, tetapi yang lebih penting adalah pembebanan pada dunia nyata itu tidak hanya satu jenis beban saja, Hans. Untuk satu jenis pembebanan, ya 3 titik ini 3 batang ini 0. Tetapi untuk pembebanan yang lainnya bisa jadi 3 batang ini tidak 0. Kebayang ya?
Oke, kebayang.
So just now what I explained to Hans is Hans asked me whether if it's zero force member, so it is under tension or compression. No, it's neither of those. Okay, which means that there is no load there, so it's not under tension or it's not under tension, and it's not under compression as well. the zero there, the load there is 0. Okay. In the real world, sometimes we will find out that this kind of condition is happening at certain member. But most of the time, you will not be, it is better for you to not just taking out those member. Okay. Why? Because like what Hans said before, okay, the weight of the member itself is actually giving force there. So most likely there will be no zero force member, no zero force member in the actual world, yes. But the better explanation is in the real world, normally the loading condition is not just one type of loading condition. There are so many kind of loading condition that can happen at one particular structure. So for example, if it's zero force member in one particular loading condition, most likely in the other type of loading condition, it will not be zero force member. It will not be zero force member like that. Okay. Nah, ini saya coba jelaskan terkait dengan zero force member ya. So this is the last thing that I will explain to you guys, okay, about zero force member. Okay, what is zero force member and how to analyze it? At the beginning of our when we take a look at the problem. So the first thing that we're supposed to do when we try to solve a truss problem is to try to determine the zero force member. If there is a zero force member, try to eliminate those members first, because we do not need to solve it anymore. It will make our calculation much faster as well. Okay, so how can zero force member happen? Okay, if only two non-collinear members form a truss joint and no external load or support reaction is applied to the joint, the two members must be zero force member. This is the example. Okay. Try to take a look at member ED and member CB. Okay. Those two members are joining together at joint D. And there is no external forces happening at joint D. Okay. Most likely, member CD and member ED, it will be zero force member. Both will be zero force member. Okay. The example here, anyone here can find the example in this particular problem. Which part of it is zero force member based on this particular definition? Two non-collinear member from a truss joint. Collinear member means like this. If we have collinear member, it means, for example, this one is AB, this one is BC, and the joint is over here. These two members is collinear member. So in the same line of action like that, it's collinear member. So if only two non-collinear members form a truss joint and no external load or support reaction is applied to the joint, the two members must be zero force member. Can anyone here point out which zero force member that follows these particular rules?
I'd like to try, sir.
Yep. Of course, you can, Rafi.
Could it possibly in the joint A?
Joint A? Yes, correct. Joint A. AF and AB, you mean, right?
Yes, sir.
Yep. It's correct. It's follow these particular rules for zero force member. So we have AF, which is perpendicular to AB, which means there is non-collinear. Those two members are non-collinear, and there are no external loads happening at joint A as well, which means that AF and AB, those two members will be zero force member, right? Okay, Rafi, can you find another one? Or anyone else here? Can anyone else here find another zero force member?
Possibly joint DE and DC, sir.
DE and DC, yes, correct. DE and DC as well. So beside this one, beside join A, you can take a look at join D there. There is DE and DC, and those two members are non-collinear. And there is no external load happening at join D as well. So this and this will be zero force member. This and this from the previous one will be zero force member. So those four are zero force member. Okay, those four are zero force member. Okay, good, Ravi. Yeah, those four are zero force members. So basically, if we try to analyze a case first, so if we have a problem, for example, like this, and the first thing that you're supposed to do is to try to analyze whether it has zero force members or not. If yes, then try to simplify the problem. In this case, we can simplify the problem into this. Delete all those zero force member. You can just delete all of those zero force member. Okay, in our statics analysis, yes, you can delete the zero force member. But in the real world, don't do that. Okay, so in our static analysis, we can do this. Delete the zero force member. So now we only left with this problem. This much simpler problem. Okay, you get it, guys? Okay, any question here? Any question? Okay, I believe most of you must understand about it already, then I will continue then. Now we go for the other definition of zero force member. Okay, any of you can try to analyze this particular problem here and check whether we have zero force member. But this one is the other definition of zero force member. The definition here for the zero force member that is happening here is slightly different than the previous one. But we have a zero force member here. Anyone here can help me to determine which member is the zero force member. In this particular case, try to analyze, try to use your engineering sense. Hello, 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 no one? Judy, hello, Judy.
Yes, sir.
Okay, do you have any idea which member is your first member? Hello, Judy?
Can it be E?
E? No, it's not following the rules because there is an external force there, Judy, right?
Yes.
If there is no P there, there is no external force P there, yes, ED and AE will be zero force member, but there is an external force P there. So ED and AE will not be zero force member, Judy, okay? Hello, Judy?
Yes, sir.
Try to take a look at join D, Judy. Try to take a look at join D and try to implement, for example, this one is our X direction, sorry. This one is our X direction and this one is our Y direction. Try to implement sigma Fx and sigma Fy there. I believe you will be able to find the zero first member of there. Or anyone else as well. Try to take a look at join D and implement sigma Fx and sigma Fy, but using this coordinate instead. Using this axis instead. Can anyone
AD.
find out? Yep, Aurelia.
AD,
Yeah.
AD non-zero member, sir.
Non-zero or zero?
Oh, sorry, zero force member.
Zero force member. Yes, AD is zero force member. How can it be? Try to take a look. If we use sigma Fy equal to 0, okay, in that direction, in the direction that I draw, right? What we have is only FAD there. If we take a look at the join D, the free body diagram will be like this, right? FDE, FCD, and this one FAB. Sorry, AD. Okay. If you try to take a look at the sigma Fy equal to 0, what you will have there is FAD only. There will be only FAD. FAD will be equal to 0. So FAD here will be zero force member. Okay. What else? Using the same method, anyone here can find another zero force member in this particular problem. There is one more zero force member that we haven't discussed about. Anyone here can find out the zero force member, the other zero force member. Hello, hello, hello.
Is it AC, sir?
AC, yes, correct. It's AC. Thank you, Ricky. Okay, so the same for AC. The same for AC, right? Take a look at joint C. Try to use the same axis there. Okay, try to implement sigma Fy equal to 0. Okay, try to implement sigma Fy equals 0. What you will have there is FAC sin theta equal to 0. In this case, FAC will be equal to 0. Okay, we only have 5 minutes right now. So this is it. This is all the definition of zero force member. This is the first definition of zero force member. If you have two non-collinear member met at one joint and there are no external load or support reaction, then those two non-collinear members will be zero force member. But the other one will be this one. Okay. If we want to simplify this case, we can simplify it like this. Okay, we can simplify it like this. Because AC and AD is zero force member. And for this one, the definition is actually simple as well. If you have a collinear member like ED and DC, and there is another member that is non-collinear to those two members, okay, and there is no external forces happening at the joint, then the third member will be zero force member. So that's the example of this and this as well. CD and CB, CD and BC are collinear, right? They are straight to each other. It's making a straight line, collinear. And there is a third member which is not collinear to those two. The third member will be zero force member. Okay. Okay, this is the things that we will discuss tomorrow. Okay, and tomorrow as well, I will discuss about the method of section. So in order to solve for Truss problem, we have two methods. The first one is method of joins. Yeah. The second one is method of section. And method of section, I will discuss the method of section more. Okay. I think that's all for today. Okay. Thank you very much for listening. Okay. See you guys tomorrow morning at 7 in the morning. Okay. See you. Bye.
Thank you, sir.
User.
Thank you,
Sir.
Thank you, sir.
Thank you. Bye.